Thank you very much. Thank you for the invitation, and I really hope I can give a nice contribution to this interesting workshop. So, as Masha mentioned, I'll be talking about the application of swarm robotics to precision agriculture. And as Cyril mentioned, the first question to answer is why we need swarms of robots at all in agricultural robotics. Well, we know that automation is moving in very different direction from manned vehicles that can drive very fast on the field to completely autonomous robots. We believe that in both cases, having swarms or very groups of robots that operate in the field can be an advantage because on the one hand, you can parallelize operation on very large fields. So you can cover larger areas in a fraction of time, and this will lead to higher efficiency. Also, we can imagine that multiple robots can collaborate for certain actions, for instance, in the monitoring aspects or in identifying areas of the field that require better, high resolution monitoring. And this can lead to higher accuracy in the action required. Swarms, as you may know, are redundant systems, which means that removing or adding a few elements does not impact on the performance of the system. So we aim with this to a higher robustness of the system as a whole. And then what we do in swarm robotics to deploy in general decentralized algorithms that can scale well with the size of the problem, which means that we can have the same algorithms working for small or larger swarms, which can also address small or larger farms. So we have this scalability properties that is very interesting. In the last few years, I've been working on the concept of applying swarm robotics for UAVs for the monitoring of weeds in a field. You can see in this concept image the main ideas behind this concept. So these robots need to communicate with each other in order to observe the field. They may share therefore information. They may even try to intervene on the field and to some extent. In order to do that, we require specific hardware abilities, like for instance, the ability to have an high-level control for the UAV that is not anymore a passive sensing system, but is actively trying to seek information into the field. So we need a high-level control strategy, onboard vision, because the UAV must recognize on board what's going on into the field, what are the relevant features over there. And of course, we need communication between the systems in order to have some collaboration within the swarm. Then, as I mentioned, onboard vision is a complex problem. And for the case of weed classification that Cyril already mentioned, there are a lot of algorithms, which, however, must be adapted for working on board the drone and for specific tasks, like, for instance, classifying crops from weeds or estimating the density of the weed in certain areas. If we are able to have these two components, then we can develop the swarm level control aspects, which go from the collaborative identification of weeds, the covering a large field with multiple robots, and deploy the right amount of UAVs in different areas of the field. So today I'm gonna give you some idea of the work we have been doing in these three different aspects, and we will start exactly from the crop weed detection, framed it into the swarm robotics context. We are basically basing ourselves on this benchmark problem of detecting weeds in sugar beet fields. In particular, the weeds we are looking at are the volunteer potatoes that emerge spontaneously during the rotation of sugar beets. This is a benchmark problem. There are a lot of very good algorithms and neural networks like the bonnet that we have seen in the previous talk. The main issue for us is that we have to deal with a limited computational power for UAVs that cannot fly much longer with by expanding a lot of power into the computational units. So the payload is also limited. Therefore, on board of standard UAVs, you can't expect to run very complex, very heavy neural architecture. So what our approach is then to leverage on collaboration between the UAVs in order to obtain higher quality results. So the first thing to do then is to train a shallow neural network and in order for crop width classification. And we use the faster RCNN framework with a shallow backbone, which could have good performance still with a small, relatively small computational effort. And we are not targeting image segmentation here, but what we want to do is to identify the plants, the individual plants, in order to, for instance, count them into the field. This is because we think that counting can be useful in order to estimate the density of weeds in certain areas of the field. If we ever analyze the performance of the network, we can see that there is still quite some error. The more weeds you have into the field, the wider is the probability distribution in the detection, which means that errors add on top of each other. So the idea is to exploit swarms to improve the detection of weeds by having multiple robots observe the same plants, the same part of the field multiple times and possibly from multiple perspectives. So if you imagine this, that the first drone has a certain observation into the field, then later in time another drone passes on the same part of the field and has a different observation, it is natural to think that these two information could be somehow put together in order to obtain a better classification of the plants. And in particular, what we tried is to have the output of the first classification to be an input for the second classification in order to improve over time the classification output. The concept is that, therefore, the first observation, we have no a priori information, therefore we perform a standard classification. But when the second observation is performed, we can compute a kind of probability map on the basis of what was observed before, and we can add this channel to the classification network in order to improve the second classification. And this process can be repeated multiple times across multiple observations. And we observe that as the number of observations increases, we can have an increase in the classification performance. And basically, we can match with a small neural network the performance of a larger one. So the approach is valid. We can actually do a more accurate classification by exploiting multiple observation of the field. This was just a preliminary study that we did together with Federico, who is now a PhD student in Bonn. But the idea is to extend now the study by leveraging on the fact that drones can really observe the same area from multiple perspectives, and therefore can really access to very different features, and therefore they can really obtain from multiple observation different information that can boost classification over time. So this is how you can exploit swarms for improving the accuracy of classification. Let's now go on to the collaborative mapping problem. Here, what you want to do is to create a map of the field that indicates where the infestation is higher. And as you know, in most cases, the fields are not uniform. So there are areas where there are more weeds, for instance, because weeds appear in patches. And therefore, there is the need to observe with higher resolution those areas in particular. So the problem of collaborative wind mapping can be stated as the following. We need to cover a cultivated field completely, and we need to build a map by minimizing the classification error. Also, our idea is that given that we are in a swarm robotics context, we need to aim to robustness, efficiency, and scalability. This means that we want strategies that do not depend exactly on the knowledge of the number of robots to be deployed. And also they must be strategies that can adapt to heterogeneous weight distribution, because this is a common feature. So the proposed solution is to exploit simple random walks, and in particular reinforced random walks on the basis of the information that is available to the UAVs while monitoring. A random walk is a random motion over the field. If we imagine that the field is divided in a small portion in a regular way, like it's what we call cells, then a random walk is just moving from one cell to the other until the full field is covered. Here you can see our drone performing a random walk in an indoor setting. And of course, given the randomness of the process, it may not be optimal. Therefore, we need to implement some techniques that enable us to reduce redundancy in the observation when this is not needed. But the good thing is that we can put as many drones as we want on the field, and these will somehow randomly diffuse in the field and cover the field completely. So our first approach to the random walk problem was to apply techniques known as potential fields. Basically, when we have to decide what is the next cell to visit, then we need to exploit the information that is available to the drone. Therefore, we compute a force vector that would push the drone toward the areas that are supposedly more interesting. If we assume, for instance, that the weeds are distributed in patches, knowing that in some area there have been some weeds have been observed, would push the drones to explore those areas first. But then we have also to consider that there are other drones that are concurrently observing the field. Therefore, we compute repulsion vectors from other drones in order to not to cover the same areas of the field. We compute a resultant from all these vectors, and this resultant will be a bias for our random walk. So we select a neighborhood, and for each cell within the neighborhood, we compute a probability of being visited according to the bias that is provided by the force vector. And this will somehow let us decide randomly which is the next cell to visit. This approach works, and I will show you some results later, but is not taking into account completely the information that can be acquired by the drones when they are observing the field. And it's not going actually to formally compute what is the uncertainty reduction from multiple observations. This we can do if we build a model of our sensor that tells us what is the likelihood of obtaining a certain output given a certain observation. So if we go back to our network that gave us this probability map, then we can use this in order to bias our random walk. And what we are actually doing is that when we want to consider within our neighborhood of cells one single cell, what is the likelihood that this cell should be observed the next? Exploiting our model, we can compute the residual uncertainty of about this cell, given the observation that were previously done. So, for instance, if no observation was performed in a cell, then our entropy is maximal because we don't know anything about it. But as the more observation we make, the entropy will go down. So the residual uncertainty will be smaller. And also we can compute the information gain, that is the expected reduction of uncertainty from a further observation. And this can be done based on the model of the sensor that we have. Then, of course, also in this case, we have to factor in the contribution of other drones that are observing the field at the same time by discounting the probability of visiting a cell if this cell can be targeted also by other drones. So we have basically also in this case obtain a utility for each cell, but this time computed on information theoretic measures. And therefore we can choose the next cell to visit on the basis of this utility. We have computed, therefore, the error in width mapping with both approaches and compare this with a baseline theoretical performance from a standard width pattern that is basically visiting each cell of the field an equal number of times. This is M is the number of times that the cell, each cell of the field is visited. As you can see, the baseline, the more observations are made, the error in the width recognition goes down. For what concerns the performance of the potential field heuristics, we can see that it improves, but it requires 6 passages over the field, which is not very efficient. And also we observe that this is very sensitive to the parameter selection, basically the weighting of the different vectors in order to compute the resultant. The method based on information gain instead is parameterless and provides an uncertainty reduction that is improving over the baseline after only 3 full field passages. So this means that with a very simple and noisy classification, we can reduce the classification error significantly. This is how we think that drones can monitor and map a field as a swarm. But now let's broaden a little bit the picture, because the field we are looking at may be very, very large and very, very heterogeneous. Think, for instance, to grasslands that extend over hundreds of hectares, and where weeds are present can be very dangerous to the cattle that is moving on the grassland. In this case, we need strategies for extensive field monitoring, even with a limited amount of resources. What we think it is relevant to do is, therefore, to have a decentralized deployment that considers 2 observation levels: an high altitude estimation of width density, which is, however, very noisy, and a very precise low altitude collaborative width mapping. So we imagine that UAVs can move from 2 different altitudes in order to recognize which are the areas that require a collaborative, high resolution collaborative width mapping, and therefore deploy the UAVs only to those areas. In this case, you can see that, for instance, that we can divide a larger field in a few big areas, and these few areas have different requirements. So attention should be focused only on those areas that contains width patches, and therefore the problem of moving our swarm to those areas translates into a utility-dependent UAV deployment. We address this by means of techniques that are derived from both collective decision and task allocation problems. This problem is a collective decision problem when there are less UAVs than the optimal number for a single area. So all the UAVs should be put on a single area in order to monitor this efficiently. And also, this is good when collaboration improves the mapping efficiency, because then you want many drones to collaborate. On the other hand, if you have UAVs that are in excess with respect to the optimal number, then you need to allocate UAVs to different areas at the same time. And this is also useful when the area utilities do not vary considerably over time. But in our case, the utility of an area depends on the monitoring needs, so there will be a change. The first two aspects lead us to study how to determine the optimal number of UAVs given the mapping dynamics. And the second part tells us that we need a strategy that can be easily tuned to different scenarios. In a few words, we can see that the deployment strategy that we developed see that the UAVs explore and estimate the utility of areas by flying at a high altitude, by having this low resolution inspection. We can use different techniques to do that. When instead UAVs are deployed, they have at a low altitude, they have high resolution images that can be more precise into the classification. But for doing this, we need to prioritize only the inspection of high utility areas. Given that our UAVs can communicate with each other, we can imagine that they are forming a wireless communication network and use the ability to communicate with each other in order to recruit themselves toward areas of higher utility. We also consider the possibility that UAVs are inhibited from other UAVs in monitoring certain areas. And we can consider here two cases. In one case, it's a UAV is notifying another UAV about the fact that the area that it is monitoring has higher utility than any other area. Therefore, it inhibits other UAVs to monitor different areas. On the other hand, if there are too many UAVs deployed in one area, there is a kind of self-inhibition among UAVs that are in the same place, so that the optimal number of UAVs is achieved. We therefore develop a probabilistic finite state machine for the individual behavior that can give us this feature. So we can consider UAVs that can be in two states. Either they're uncommitted, and this is when they are performing the high altitude inspection, or they are deployed to an area and they are performing the low altitude mapping. In this case, they can also recruit or inhibit teammates. And there are two kinds of transitions: a deployment transition from uncommitted to deployed, which can be spontaneous based on the individual estimation of utility of an area, or interactive through recruitment. And then there are an abandonment transition for which deployed agents become uncommitted again. And this is, can be also spontaneous, for instance, when the mapping is completed, or interactive by means of the inhibition mechanisms I was mentioning before. This behavior is derived from the decision-making abilities of honeybee swarms, which we have studied extensively, and which we deployed in robot swarms for collective decision-making. So we know this behavior very well, and we adapted it for the case of UAV deployment in the field. So I'm showing here the feature of this algorithm in different situations. Now consider that there are three areas to be inspected, A, B, and C, which starts at different utility. So 1, 0, 7, and 0, 4, for instance. And now we want to monitor what is the fraction of the population that is deployed to the areas, different areas, by following this algorithm, this simple algorithm. We consider the case in which there are no interactions between the robots. So this R equal to 0 implies that only spontaneous behaviors are performed. There is no recruitment, no inhibition. And we have 50 robots, which is the optimal number for an area. we can see that by means of the probabilistic decision making, the utility-dependent probabilistic decisions, robots get enrolled into the three different areas, A, B, and C, with a more or less proportional deployment to the utility. And given that there are no interactions, once deployed, they are not moving away from the area unless the area inspection is completed, which is when the utility goes down to 0. This is because the more they inspect, the more they monitor, the lower the utility to remain in the area is. Therefore, this is a kind of utility proportional deployment. But if we enable interactions, so we have here recruitment and cross inhibition, we can see that there is a winner-take-all strategy that emerges where all the swarm goes in the first area, the one with the highest utility first, and it stays there until the inspection is finished. Then the whole swarm goes to the second area and then to the third. This winner-take-all strategy is because we have just the right number of UAVs to optimally monitor an area, a single area. If we increase the number of UAVs to 75, then we see the situation slightly changes. When there are no interactions where it is pretty similar, they are still deployed proportionally to the utility. But when we enable interactions, we can see that the optimal number of robots get deployed to the area with highest utility until the utility of this area is still pretty high. The remainder of the robots, which are 25 robots, it gets deployed to the one or the other low utility areas. When the utility of the area A goes down, then there is a redeployment that is happening. So robots from this area get deployed to the second highest utility area and then to the third. So we have a utility dependent deployment which stays reactive to the actual demands from the field. And this was achieved only by changing a single parameter in our system. This is a self-organized strategy that can be exploited with the UAV swarms having some limited information about the field and some limited communication abilities. So to sum up, I've been showing that we can actually deploy swarms of UAVs on agricultural field, and we can obtain higher efficiency both in time and in accuracy, thanks to parallel operation and collaboration. These strategies are robust to the failure of some UAVs, are scalable, so we can vary the group size in real time and still they work. And then to address the problem of monitoring very large fields, we are proposing a decentralized deployment, redeployment that is completely self-organized and can bring the ability to focus only on area of high interest, enforcing also a utility responsive behavior. Thanks a lot for the attention. I hope I stay within the time allotted, and I'm happy to take any questions.